the electrons are no longer just attracted to the nucleus, but they're also repelled by each other. Right? So we now have to deal with how do we fit two electrons around a proton, and how do the physics or the orbitals or the energy level change? How does the structure change of helium by adding that additional electron? And the problem, as we're going to see, is that we can't tackle the problem the same way we did for hydrogen. I can't just write down a Hamiltonian and solve the wave functions for it. In fact, the solutions will not be available to us. And I'll explain why that is today. And instead, we're going to have to start thinking about ways to approximate things about atoms. And we're going to find that in general, if there's more than one electron in a system, we can't solve it exactly. Okay? No possibility. So we're going to have to resort to approximations. And using helium as our motivator for approximations is a really good thing because it's the simplest two electron system. Okay, so when we get to hydrogen, molecular hydrogen, H2, that also has two electrons in it. But in the sense that it has two atoms, two hydrogen atoms separately, they're going to bring together. So whatever happens when they come together involves two hydrogens. So if we understand how, if we have a system that always has two electrons in it, always something that has two electrons in it, like a helium atom, we understand how to do good approximations for helium. Maybe we can apply those things to molecules. This won't be that much of a stretch. But we first need to understand why the problem fails for helium. Why do we have to resort to approximations? That's going to be our goal today. And we'll start setting up these approximations, and we'll learn a few things about the way electrons work that will help us guide us to coming up with the right approximation, the right guess. And we can make any guess we want, but only one is going to be really good. The rest of them are going to be crap. So we need to identify what that strategy is for approximation. All right, so let's start talking about helium. Right? Helium really isn't so much different from hydrogen. Well, other than it has an additional electron and an additional proton, right? So helium, let's embed it into a coordinate system just like we did before. We're going to put a nucleus in the middle, or origin. And of course, the nucleus has two protons in it. Helium-4 also has two neutrons, but we don't care about them. This is what's called helium-4, right? Which is the most common form of helium. It has two neutrons, but again, neutrons don't have a charge, so they don't interact with the electron electrostatically. Okay, they're just additional masses that sit in there, but we have to consider them for the mass of them. If we wanted to calculate the mass of the nucleus, we have to consider that there's two neutrons in there as well. All right, but they don't involve, the only time neutrons interact is through the weak interaction, not through the electromagnetic interaction, because they're uncharged, or the strong interaction, which are not relevant to us. So we've got this extra fat nucleus in the middle, and it's looking, and it has two vectors extending from it, displacement vectors for these two electrons. So somewhere in space we have an electron that will mark its location with R1. Call that electron E1. And then we have some other electron in some other direction, which we'll call E2. And it has displacement vector R2. Okay. We should, right? So that, right, if we think about the terms in our hydrogen Hamiltonian, right, which are the angular momentum of the electrons and the electrostatic attraction to the proton, these are all the coordinates we need. R1 tells us everything we need to know. Right? We can use R1 to track the angular momenta, the orbital angular momentum. We can also use it to measure the radial potential, the electrostatic potential. But there's an additional force in this problem that introduces a new coordinate, which is the repulsion between the two electrons. Right? So we need to track the relative position of the two electrons as well, because the term involving the repulsion between the two electrons obviously depends on their relative position to each other. So we're going to introduce a new coordinate to the system, which is dependent on the other two. We'll call that, we'll draw a vector. Sorry, that's a really bad arrow. between the two electrons, which we'll call R12, right? And we have, so basically R1 in spherical coordinates is the value of R, R1, theta 1, phi 1. And R2 has a different coordinate system or a different coordinate component, different components, R2, theta 2, phi 2. And then R12, just by vector construction, it's just the absolute value of R1 minus R2. Okay, that's just what you get from addition of vectors. The relative coordinate is the difference of the two coordinates. Okay, so we have essentially, this is a 6-coordinate problem, 6 different coordinates, but we also have this additional relative coordinate that we're using to track the electrons. Okay, but it's dependent on the others. So this is a 6-dimensional problem. Right, and so we can write down an energy Hamiltonian for this, an energy operator, right? And let's just write it very simply, right? Let's just write down, not in terms of equations or anything, just the individual qualitative terms that we expect to contribute to the energy. Well, the first one, of course, would be the kinetic energy of electron 1, the kinetic energy of electron 2. We've got 2 kinetic energies, right? And we know those to be in some sense, the angular motion, the angular kinetic energy of the electrons, as well as the radial, how it's moving in the radial direction. And each of these electrons are attracted through potentials to the protons, as well as repelled by each other. So we're going to have 3 potential terms. So that would be between E1 and the nucleus. A potential term, sorry, it's not a bar, but a caret, so an operator. Plus the attraction between the nucleus and the second electron. And finally, we have a final potential, which is between the 2 electrons. Okay. So by definition, these are attractive, the nuclear terms, right? Because the nucleus is positive and the electrons are negative. So that means that these are less than 0. But the electrons repel each other, right? So this is a repulsive term. And it's always greater than 0. That's all we have, right? 5 different forces, 2 kinetic energies. Well, sorry, 3 forces and 2 kinetic energies, 3 potential energies, which all have the same formula. This one is positive and these are negative. Okay, that's the only difference. Because the charge of the electrons are the same as the charge of the nucleus, except there's 2 protons in here instead of 4, or instead of 1. But besides that, these are negative and this one's positive by definition. Well, I can rewrite this a little bit, right? If you think about it, other than this term, if I turn this term off, in some sense, I have an electron kinetic energy and a potential energy which only depends on electron 1, and 2 terms that only depend on electron 2. Okay, so I could separate these terms. Let me just rearrange things. In some sense, I have T plus V for electron 1 plus T plus V for electron 2. And then I have this extra term that interacts the 2 electrons. So this is my interaction term, which is repulsive. And then what do these look like? Well, this is the kinetic energy of an electron around a nucleus, plus the attractive potential of an electron around a nucleus. And then I have the same term for another electron. These terms by themselves, if I got rid of one of the electrons, if I just did this, and I just have the E1 term, I just have the Hamiltonian for hydrogen. Right? All hydrogen is a kinetic energy for an electron and a potential energy for an electron around that proton. So this is hydrogen for one of the electrons. Here's hydrogen for the other electron. And then I have this term that couples them together. So what I could write is that this Hamiltonian is a Hamiltonian for a hydrogen atom centered at electron 1 plus a hydrogen Hamiltonian centered around electron 2 plus this interaction term, which we'll call V12. All right, so if I turn this interaction term off and I say the electrons aren't interacting with each other, the helium Hamiltonian looks just like two hydrogens put together, right? It's almost as if I took the proton and electron of one hydrogen and a proton and electron of another hydrogen, and I jammed them together in the same space and added them together. The total energy of the system uninteracting for helium just looks like two hydrogens in the same place. That's cool. That's a nice way to start thinking about it. We know how to solve this problem. We know the energies for this, just the hydrogen energies. We know the wave functions for this electron. They're just the hydrogen wave functions. And the idea is that the majority of this Hamiltonian is just hydrogen-like terms. Right? We've got two electrons that act relatively independently of each other, as if they're hydrogen. And then we have this interaction term here that brings them together. And this interaction term is never zero. Right? So in some sense, the energy or the Hamiltonian for helium looks like two hydrogens with an extra fudge factor that compensates for the fact that these two electrons see each other around the proton. So let's do, here's a way to tackle this problem. What if we say, hey, the two electrons don't interact? Let's just turn the interaction off and ask, what's the energy of the helium atom? Right? Well, the energy of the helium atom, both of those electrons are in a 1s shell. It's 1s2. That means that effectively, if we turn the interaction off, helium is just the same energy as two hydrogens in a 1s limit, in the 1s shell, right? So we have two 1s hydrogens that we're putting together into this helium atom and pretending that the two electrons don't see each other. Okay. Let's just see how good that approximation is. Let's see if we get close to the right answer, because we can measure it experimentally, right? We can always go to experiment and ask something about helium. What are your energies? With spectroscopy or with ionization. We can always measure that very accurately. So let's make a prediction of what we expect to see by assuming that the molecule, the atom, the electrons are not interacting. Okay, so let's go ahead. And this approximation I like to call the orbital approximation. What we're going to assume that V12 is basically zero, so that the Hamiltonian for the helium atom looks like the hydrogen Hamiltonian for one electron plus the hydrogen Hamiltonian for electron 2. Okay. And let's assume a helium atom in its ground state which is 1s2. Okay. So that means that the wave function for electron 1 is just the wave function of the 1s orbital, which, as you know, is just a function of r. Right? It's a sphere. And sorry, it's localized at R1. And psi E2 is a wave function, 1s orbital for hydrogen, and these are the hydrogen orbitals at R2. And this would mean then that the energy of the helium atom is the energy of the 1s state for electron 1 plus the energy of the 1s state for electron 2. And that the wave function for helium, the total wave function of the helium, is equal to, call it psi1 at R1, psi2 at R2. Right? So these are our 1s orbitals. So when you have a system, and we saw this with the when we did normal modes for vibrations, if you have a system you have a bunch of different degrees of freedom, here the degrees of freedom are the 2 electrons, a bunch of degrees of freedom non-interacting, then the total energy is just the sum of the individual energies, and the wave function is the product of the individual wave functions. So anytime we have this, we have this. Okay? These are always go together. Summing 2 electrons, having a sum of 2 energies with non-interacting leads to a product of the wave functions. Right? We don't have to do any math here, right? All we have to do now is say the energy of the 1s2 state of helium is just the energies of the 1s orbitals times 2. Well, the energy of a hydrogen atom for a hydrogen-like atom, right, is z squared, where that's the charge of the electron, times the Rydberg constant, divided by n squared minus. And so this is z squared, and we'll just minus z squared over 13.6 eV divided by n squared. Right? 13.6 is that Rydberg constant electron volt, right? It's a 109,600 wave number. I'm just converting it to a smaller number. Right? And Z is the charge of the nucleus. So for helium, then, the energy of the helium atom in the 1s2 state in this prediction would be 2 squared minus 2 squared, because Z is 2, because there's 2 protons, times, times 13.6 eV, times 1 over 1 squared plus 1 over 1 squared. Right? That's the 1 over n squared. Right? We're going to add the 2 energies together. Each one gives me a minus 1 over n squared. And so I'm going to get a sum, right? But this is 1 over 1 plus 1 over 1, right, which is 2. So what we get is that the total energy of helium from this approximation is minus 8 times 13.6 eV, which is minus 108.8 eV. Right? So just by making a very simple assumption, by turning off the interaction of the 2 electrons, we get a number, right? Just from hydrogen. Right? This is, again, the building up that I like to do in quantum mechanics, this bootstrapping. We start with a simple problem we understand and treat more complicated problems with combinations of the simpler problem. We'll see that in molecules, especially. That's going to be our tackle. That's how we're going to tackle out our molecules, is by just taking simpler orbitals and adding them together to make it more complicated. And so we get a prediction of minus 108.8 eV. Right? Remember what this means. This means that the ionization energy, the energy to remove 2 electrons from helium, is 109 eV, roughly. Right? So what this means is, let's go to the next page. If the energy of the 1s2 state is minus 108.8 eV, then the energy required, or the voltage required, to take helium and remove 2 electrons, the energy required here is 108.8 eV. Okay, so what we're going to do in our experiment is take some helium gas and run a voltage through it. So we've got this tube of helium gas. That I'm going to run a coil through, electrical coil. Well, sorry, we have a negative charge here and a positive cathode here. Right, and we're going to run a voltage through here. We're going to run a voltage through here, and inside of this we have helium. Right, this is what's called a helium atoms. What we're going to do is do a little experiment. We're going to vary the voltage, and we're going to look at the current. All right. When the first electron leaves, right, we're going to sweep the electron. Right. First, we're going to kick out the first electron. When the first electron gets kicked out, the current will increase because now the electrons are flowing. All right. So when we see the first current jump, we know that the first electron comes out. But we have 0, 0, 0 current, and then we hit 24.6 eV, and we see a current jump. That is the first ionization, right? So now we have neutral helium here, and now we have helium plus here. And we continue our current, and then at 54.4 eV, we get another current jump. This is He2 plus. So the first electron leaves at 24.6, and the next one leaves at 54.4. So delta E experiment is 54.4 plus 24.6, right? Which is 79.0 eV. So experimentally, the result is 79, but our prediction is 109. Right? So the experimentally, the electrons in helium are bound less strongly than we predict. Right? And so what does that mean? Well, what would make the electrons easier to remove? Well, if they're not as strongly bound to the nucleus. What would make them less strongly bound to the nucleus? Repulsions to something else. What did we turn off in this example? We turned off repulsions. The electrons don't repel each other. So this energy difference is entirely due to that extra interaction term, that V term, the repulsion term. So what this is telling us is that the repulsion energy is about 30 eV. It's the difference of this. Okay, so the electron repulsion energy would be V12 for the 1s2 state is about 109 minus 79 eV, which is about 30 eV. Right? That's a lot of energy, right? Compare that to the ionization of hydrogen, which is 13.6 eV. So the amount of repulsion between the two electrons in the helium 1s state is twice the attractive energy of the electron to hydrogen. That's a lot of energy. There's more repulsion in helium than there is attraction in hydrogen. It's a very important, obviously it's a very important contribution. Right? When the repulsion is on the order of the canonical attraction of an electron to a proton, that means that it's a big effect. Right? We're way off, very off. However, that's not to say that we're not doing that badly. We're not doing terribly, right? We're still kind of in the factor of 2. You know, that's not too bad. There's certainly, I'm sure you guys have done chemistry labs where you've gotten numbers that are way off of factor 2 what they should be, including in this course. So we're doing pretty good for a really dumb, naive approximation, but that's not what this class is for. We've lost so much precision because for the last 2 weeks we've been talking about hydrogen, and everything that we predict about hydrogen is exactly what we see in experiments, precisely. Here we go to the next atom, so literally the next simplest system in chemistry, and now we've gone from perfect precision to close enough, right? Not good for me, not good for any of us. There's no predictive power. But it does teach us something about what we're doing wrong. Right? We have to pay attention to this repulsion energy. Electron repulsion is important. So what we need to do now is to think about how we implement and account for this repulsion in our system. How can we make a better guess? Right? In order to do that, we have to come to spin. We have to think about how electrons interact with each other. Right? So we need to be much more careful. We need to understand exactly how two electrons can interact with each other in order to really understand this interaction term. Right? We're missing some subtleties. So I want to introduce those subtleties today. And we won't be able to do the better calculation today. We'll do it next class. But we'll get it set up today. If we should have the time to set it up. But I want to teach you a little bit about the subtleties of electrons, which will help us so much when we get to molecules. Right? Because this is exactly the same kind of argument that quantum mechanicists and quantum chemists and physical chemists went through in the early 1930s. When quantum mechanics became mainstream, people, normal scientists were starting to do quantum mechanics. Chemists want to calculate the structures and energies of molecules, the properties of molecules or big atoms. They went through this exact process, right? The first thing they tried to calculate the energy of helium is just, well, let's just treat it like two hydrogens and then turn on or turn off this interaction. And they find that, again, you get something reasonable, but not really that good. It's not up to our standards. And so this iterative process of improving our understanding of electrons, which is something that was developed in the 30s and the 40s, will help us guide us to the right guess. That's our goal, is to build the right guess. So this next approach, which is what we're really going to focus on, there's a couple different terms for it. I like to call it the independent electron approximation. All right, what we're going to do instead, we'll hold on to the fact that the electrons might be contained in these orbitals that look like hydrogen 1s orbitals, right? In some sense, the helium 1s state orbital doesn't really look any different from the hydrogen. The wave functions are very similar. They're still spherically symmetric. They still should look like each other. But we haven't considered what we have done is we've, in some sense, locked our electrons into identities. We say, hey, here's electron 1 and here's electron 2, right? None shall the twain swap. They're independent from each other. They can't do anything. They're independent, distinguishable electrons. That was what we did in the orbital approximation. So we got electron 1, we got electron 2. They're completely different things. They have the same properties, but they're entirely different objects. That's our failure. They aren't entirely different objects. They're not distinguishable. The key part, and this is what we learned in the 30s and the 40s, by we, the royal we, I certainly didn't. The key insight is that all electrons are, and this is true for anything, not just electrons, protons, atoms, molecules, it doesn't matter. But we're just focusing on electrons here. We could say all particles, quantum particles, not just electrons, are identical, which we've already assumed, but the more important thing is that they're indistinguishable. If G and Charlie are both electrons, it's very easy for me to distinguish between the two. Very clearly, Charlie is very clearly G electron. There is no difference between them if they were actually electrons. There's literally no difference. I cannot name an electron, electron one, electron two, and watch them track around. It's impossible. Statistics don't work that way for electrons. They just don't work that way. Every electron is exactly the same. I mean that, exactly the same. You can't label them. So what that means is that imagine, for instance, you took a snapshot and you could measure electron one and electron two, but you can't do that. There's an equal probability you take that picture and it's actually two over here and one over here. You can't actually tell, right? Because they're exactly the same. They have the same charge, they have the same mass, they have the same energy. Everything's exactly the same. You can't name them. They're indistinguishable. So the fact that we've localized electron one here and electron two here is our failure. Because electron one can be electron two. We can put electron two into orbital one and electron one into orbital two. And vice versa. We can swap them. And we have to do that because that's what electrons do. It's a part of their identity. Right? It's a key part of the electron physics. And that's not what we took in the orbital approximation. That's not what we considered. We considered electrons that were distinguishable. We labeled them one and two. But we have to consider the wave function where we've swapped them as well, two and one. So there's a swap, an exchange that we have to consider, electron exchange, where the electrons can exchange with each other. And it turns out that this exchange actually contributes to electron-electron repulsion. In fact, it's very subtle. And we won't quite be able to get into these details, but there's actually a component with the exchange, right? The exchanging of electrons arises from repulsion. Two electrons will exchange to reduce their repulsion. So there is an attractive part. Repulsion, in some sense, our exchange is an energetically favorable process. It's actually tropically favorable. So it's favorable, but it arises because of repulsion. So electrons will exchange with each other to lower their repulsion energies. So that every electron will repel each other. Every positive charge, every negative charge will repel a like charge. But when it comes to electrons, they have the additional ability, because they're indistinguishable, that they can exchange, and that exchange actually reduces the amount. It helps them separate in some sense. Right? If they can't move away from each other, well, one thing they can do is swap. And that swap plays a big role in the physics of multi-electron systems. It's essential. Because if we don't assume that they can do that, then you get the wrong answer every single time. Don't get the right answer. Right? And it took chemists or physicists, let's say chemists. Oh, Douglas Hartree, a chemist. It took them almost 15 years to figure this out after we understood hydrogen. And one of the things that we learned is in the 1930s about how the structure of an electron actually works. And a really great physicist from England named Paul Dirac, who is not as appreciated as the other physicists of the era. Hear about Niels Bohr and Heisenberg and all these guys. Paul Dirac, in some sense, is the culmination of the first generation of quantum mechanics. He's the bridge between the golden age of Einstein and the modern. And what Dirac did was consider the fact that that electrons are moving often relativistically near the speed of light. They're not moving very slowly, they're moving very fast. They have special relativity. Special relativity affects their physics. And when you account for the fact that electrons can be relativistic, meaning that they move near the speed of light, you learn very interesting things about them. Very interesting properties arise from the fact that they're relativistic. Now, we're not going to derive these things, because actually it's about 3 years above this course to derive this result. In fact, we don't even learn the proof of this in chemistry, we learn it in physics. But Paul Dirac derives this theorem called the spin statistics theorem. Which is that any wave function that describes multiple electrons I'm going to use a different word than electron. I'll define it for you once we write it down. Multiple fermions I'll define this word for you afterwards. Right? An electron is a fermion, as we'll see. Must be antisymmetric. That's a new word. Upon exchange, and that's swapping, of two fermions. Right? So we'll talk about what that means in a second. And there's one other term or one other statement, which is that any wave function that describes multiple different term bosons must be symmetric upon swap of two bosons. All right, so what the hell is a fermion? What the hell is a boson? These are generic statements about particles, right? Particles and subatomic particles or microscopic particles fall into two classes called fermions and bosons, right? Two different kinds, and they have different types of properties. These are the different properties. Fermions are antisymmetric and bosons are symmetric. That's the difference between the two. And what fermions are, it's a fancy word. It's named after Enrico Fermi, who is the discoverer of nuclear fission. He created the first fission reactor. He's the one who split the uranium atom and made it go critical. Named after him, he did a lot of work with electrons and what are called fermions, named after him. And they're particles with half integer spin, like an electron. Particles with half integer spin. All right, so what are some examples? Well, just about everything. Electrons, protons, the hydrogen atom. What else has spin? I don't know, chlorine 35, etc. There's lots of different fermions. In fact, most of the particles in the universe are fermions. Okay, very few are not. There's far fewer bosons than there are fermions. And then bosons, named after an Indian physicist named Bose, who actually collaborated with Einstein to study these bosons. He worked with Einstein on this. Are particles with integer spin. Now, we haven't seen a particle with integer spin yet, but they exist. Some things that are particles of integer spin are the helium atom, carbon-12. The photon is a boson, and etc. So there are very few fundamental particles like electron or subatomic particles that are bosons. Very, very few. And there's really important reasons for that are way beyond this class. The most important boson, I would say, in physics, other than the photon, is the Higgs boson, the God particle, as they call it, the last one we've discovered. That's a boson as well, uniquely so. It has a spin of spin of 0. Carbon-12, for instance, has a spin of 0. It has no spin angular momentum. So that in carbon-12, the spin of the nuclei cancel out the spin of the electrons. It has no total spin. It's very interesting. Same with helium-4. All right, so what does it mean to be antisymmetric or symmetric upon exchange? So let's talk about it. Very, very simple algebraic property. So a symmetric wave function satisfies this property, right? So let's imagine again I have one orbital that tracks electron 1 multiplied by another orbital that tracks electron 2. This is equal to plus the wave function combination where the electrons have been swapped. Okay, so when I take the two wave functions that have two electrons in them, and I swap those electrons, I get the same functionality. Nothing changes. Okay. That's what we had before, right? Remember, this is exactly what we had before. This was our, right, for our helium atom, this was our orbital approximation. For helium. We created a symmetric combination of two hydrogen wave functions that's such that if we were to swap the electrons, we get the same wave function back. It's a symmetric combination. All right, we made this symmetric product. All right, an antisymmetric wave function gives you a negative sign instead. So if we initially have a system where the wave functions are tracking the initially labeled electrons, and we swap them, we get a negative sign. Right? It changes sign. All right, it's an odd function upon exchange, if you will. Odd upon exchange versus even upon exchange. All right? This is not what we had before. Before, we just multiplied two functions together, and when you swap the electrons, you get the same functions back. It's even. Very easy. We did not have this property. All electronic wave functions have to satisfy this. Right? Because electrons are fermions, any psi that describes helium must satisfy antisymmetry. This is our problem. We did not construct the wave function correctly. We didn't combine our hydrogenic wave functions together correctly. That might be one of the things that we consider. So we need to reconstruct the way our gas looks like so that it satisfies this antisymmetry property. Right? We can't just take a positive symmetric product of wave functions. We have to antisymmetrize them. Right? That process is actually fairly straightforward mathematically. But for this example, I want to walk through step by step. Right? And what we're going to do to understand an antisymmetry is we're going to take advantage of the spin of the electrons. This is a product, as the statement says over here. The spin statistics theorem says that the antisymmetry or the symmetry properties are determined by the spin of the particle you're representing. So, but the point is that we have not even talked about spin yet, right? We've just treated the electrons in our approximation as two negatively charged particles, but they have this half integer spin that we haven't accounted for. So what we should do is modify this, just like we did in spin orbit coupling. Let's modify our spin-free approximation by adding spin and constructing our spin representation so that it's antisymmetric like it should be. So that we get a negative sign when we swap two electrons. So what we need to do is add. So their goal now is to construct a product wave function that is antisymmetric in the spin part. When we swap electrons, we get a -1 in the spin part of the wave function. But let's go ahead and set that up. Dealing with spin is very simple because spin, and especially for electron spin, is extremely simple because there's only two states. right? There's white and there's black, right? So all we need to do is specify a white state and a black state. Make sure that they're normalized, and that if you integrate them, you integrate the square of one, you get one back. If you integrate one times the other, and a product of one of spin up versus spin down, they're orthogonal, you should get a 0 from that integral. All right, so we just need to construct, and basically we just need to add color to our electrons here and make sure they satisfy the right properties. I wanted to add something. In problem set 1, one of the last problems in problem set 1, where you've taken a white electron and you rotate it, or sorry, you take a white plus a black electron, it's a superposition, white plus black, and when you put it into the color box, it comes out white minus black. You get this additional negative sign come out. This is that negative sign. What you're doing in the color box, when you take an electron that's symmetric, white plus black, because of the antisymmetry property of spin, when you put that in there, you swap the electrons and you get a negative sign. So white plus black goes to black minus white, or white minus black. Doesn't matter which way you do it. Right? This negative sign has always been in the physics that you guys have done. It's just we didn't really quite appreciate it at the time. Okay. So this is built into all those color matrices and all those operations you did in problem set 1. That negative sign is in there. It's implicit in the math. Now we got to bring that math in, right? We need to make sure that we take advantage of all the properties of spin and that we represent it correctly. Okay, so let's define our spin. Define our spin orbitals. Okay. Assume electron I is represented by a spatial wave function, which is our normal wave function, psi I r sub I. So this is our normal wave function. If m sub s for electron I is plus 1/2, meaning it's spin up, the wave function for electron I is psi I r sub I times this alpha sub I, right? And this is our spin up orbital. Call it alpha. Right? So if it's a spin up electron, we just have this additional function we multiply that we call alpha. Okay? So alpha means spin up. That's all it means. Right? It doesn't have anything else other than that. It's just a labeling. Okay. So labeling, it says that the ith electron is spin up. If it's minus 1/2, which is spin down, the total wave function for this electron is its spatial part times beta. Beta is just a label for spin down. Okay. And alpha and beta satisfy two properties. Or they satisfy this property. Satisfying. Yeah, two properties, sorry. That the integral over alpha complex conjugate alpha dx over the space of the problem is equal to beta dx, which is equal to 1. And that's one property. And the other property is that alpha beta dx, which is equal to beta complex conjugate alpha dx, is equal to 0. Okay, so they're orthogonal. right? This is again just the color basis, right? This is the same thing as writing white, which is alpha, as 1, 0, and black, which is beta, which is 0, 1. It's the same statement. Okay, that's all we're writing. All right, so all we're doing is we're just appending our white and our black labels to our electrons. Okay, that's all we're doing. So this is a white electron localized at R1 or Ri. This is a black electron localized at Ri. Okay, none shall the twain meet. Now here's the important part. Right, well, actually, we'll come back to it in a second. So what I want to do now is I want to create a new wave function for my helium atom, which has 2 electrons in it, that satisfies my antisymmetry property. All right, so I'm going to take a psi for electron 1, and it could be alpha or beta, but don't know. Take a psi for electron 2, maybe alpha or beta, and I'm going to combine them in a specific algebraic way to ensure this antisymmetry property of the total wave function. Right? I want to combine everything in such a way that I know I get that negative sign when I swap R1 and R2. Right, so what we need, again, is that psi1 R1, psi2 R2 is equal to minus psi1 R2, psi2 R1. Right? So we need to construct our orbitals in such a way that we always get this property. There's 4 different ways to construct a combination of 2 orbitals together. 4 different ways to combine things, right? Let's write them down with spin. Because there's only 2 different types of spins, right? There's spin up, spin down. So we're going to have spin up, spin down, spin down. We're going to have this one, up, down, and down, up. Right? There's 4 different combinations of spin, so there's going to be 4 different choices that we can pick from. Remember, our goal here is to write a wave function for the 1s2 state. Right? And we know what the electron configuration for that is. It's spin up, spin down. Right? So we know that it's going to be something that looks like alpha beta. It has to be. All right, so a couple of these choices are not going to work for us because they don't represent the right system. These are the first choices, so 4 choices. One is psi1 R1. I'm just going to make them an alpha 1 times psi2 R2 alpha 2 No, let's write it beta 2 instead. Right, so that's one of them. Okay, so that's one of our options. It's just to multiply everything together. So what happens when we exchange? We'll call this 1, this whole equation 1. When we exchange, we get psi1 R2 all right. We're not spin flipping, so it's going to be beta 2 psi2 R1 alpha 1. So we flip the electrons, right? And how do I get back to this one? Well, all I do is I just rearrange everything. Right? All I do now is I can exchange again, and I get 1 again. Right? I don't get a minus sign. Sorry, I don't want plus or minus there. I wanted to underline that plus. Right? So this is symmetric. Right? So that doesn't work. And again, it shouldn't work because this is the approximation we took before, psi 1 times psi 2, we've just appended some extra stuff on the end. Okay, so that's obviously not the right answer. Okay? But these don't change at all. Don't make any differences. The other one is swap alpha 1 with beta 1 and alpha 2, or sorry, beta 2 with alpha 2. Right, so this would be, this configuration is that one up down, and this one would be down up. Okay. Right, and this is also symmetric by the same argument. Okay, so just by multiplying our spatial part of our wave function, the r part, by our spin, that doesn't get us in the right position. Right, it still doesn't work. Right, so we have to come up with a better way to represent the wave function. Now, here's the trick. Let's do the exact same process that we did in problem set 1. When we deal with it, we have a system that is up down, right? It can also be down up, right? They're exactly the same, right? The electrons are identical and indistinguishable. So in terms of energy, down up is the same as up down. So what if we do a superposition of the two? What if we write alpha 1 beta 2 plus beta alpha 2 beta 1? Right, that would be a spin wave function that's a superposition of spin up, spin down, and spin down, spin up. So let's try the superposition instead. Well, we're going to get a factor of 1 over square root of 2 because we're adding two spin wave functions together. We're going to have psi 1 r1, psi 2 r2 times alpha 1 beta 2 plus alpha 2 beta 1. Right? So this wave function is plus up down plus down up. Hey, that's a little better. That looks more quantum mechanical. Still the same problem. When I exchange, we get 1 over root 2 psi 2 r1, psi 1 r2 times alpha 2 beta 1 plus beta 1 alpha 2. Oh, sorry, I can't do that. I'm sorry. Alpha 1 beta 2. Okay, it's not too hard to show, not too hard to see that all I got to do is just rearrange these terms like this, and I get this one. It's just a reordering. Right? So all I have to do is just reorder this. And so it's symmetric. All right, so that doesn't work. All right, hey, but there's one more. What if I take the negative? I thought my internet just died, but it's good still. All right, what happens when I exchange? Sorry, I'm about to lose internet. It's going to disconnect just a second. Maybe one day they'll have internet like 2020's internet at the school instead of. This reminds me of high school. It drops. Okay. So I'm just going to swap the spin part, right? If I exchange, I get alpha 2 beta 1 minus alpha 2, sorry, alpha 1 beta 2, right? And that's minus this. So I get an extra minus sign. So this is minus the original. I'll just write right as original, which is antisymmetric. Aha. Here's the trick. We have to consider the fact that the spins are entangled, that there's an up down and a down up that are equivalent. There are two wave functions that represent this state. And the correct wave function, at least in this approximation, is that the hydrogen wave function should be a difference of those two. You have a wave function, your total wave function of this hydrogen-like atom, two double hydrogen-like atom, that we really should represent is to have, again, two spatial wave functions, but we have two different components. One which is spin up, spin down, and it's minus the one where it's spin up, spin down, spin up. So in fact, we have, what we should get instead is a wave function that's psi1 r1, psi2 r2 minus psi1 r2, psi2 r1. Right? We want to have this anti-symmetry property of this negative sign. Have to have this negative. So we have two possibilities, two possible representations. Right? One is psi1 r1, psi2 r2, where the antisymmetry is in the spin orbitals. Right, so this is antisymmetric in spin. Or we can instead do a superposition of spatial orbitals. I'm sorry, I missed 1 over square root of 2 here. Let me rewrite this one. Or we can have psi1, psi2 plus or minus psi1 r2, psi2 r1 times alpha 1 beta 2 minus or plus beta 1 alpha 2, right? So if this is a plus combination, this is a minus one. If this is a minus combination, this is a plus combination. And these are antisymmetric in space and spin. So this is the fully antisymmetrized product. We have superpositions of the electron in one arrangement and the electron in the exchanged arrangement, and we multiply it by a combination of the spins being exchanged as well. All right, so what we're going to do now is our wave function now is a superposition of all the different possible ways to exchange the electrons, right? Different orientations of the electrons. There's a special name for this. This is what's called, and historically it's called a Slater determinant. And this is our first good approximation to the wave function of a 2-electron system. It's named after a dude named Slater. Okay, and if psi1 and psi2 are hydrogen-like, we call this the Slater orbital. get this antisymmetrized hydrogen-like orbital with 2 electrons, where we take 2 electrons and treat them both like hydrogens, put them in the same space, and allow them to exchange antisymmetrically. That's what's called the Slater orbital. This is our new approximation, right? It's not just the wave function by itself, but also the exchange, the superposition with the exchange product, and also the superposition of the spins. Now imagine you had 3 electrons, or 4 electrons, or 5 electrons, or 6 electrons. Your total wave function would be every possible combination of all the electrons being exchanged with each other. That gets very, very big and very long. If you would have, you had 3 electrons, you had psi 1, R1, you know, 1, 2, 3. You'd have the 2s and the 3s flipped. You'd have the 1s and the 3s flipped. You'd have the 2s and the 1s flipped, and so on and so forth. And then you'd have to have all the spin orbitals for that. It gets really long, really, really long. But there's a formula and there's a procedure where we take a bunch of initial orbitals, psi 1, psi 2, psi 3, psi 4, from 1 electrons, and we can put them into this formula, and it will spit out the antisymmetrized combination of all of them. Okay? There's a fixed formula for us to construct these approximations, called the Slater determinant. This is the formula that gives us this value. So we input in a bunch of psi's for 1 electrons. We put it into the Slater determinant, and the Slater determinant spits out an antisymmetric combination of all of them. And so it's an antisymmetrizer, if you will. And this is the key to understanding and calculating multi-electron systems. This is the right approximation. Now, unfortunately, I have 5 minutes, so I can't do the calculation for you today. But what I'm going to tell you is we're going to plug this in next class and do the exact same thing we did before, and then turn on, with this calculate, with this, we'll be able to turn on the interaction term. Right, so we'll calculate how the interaction term affects this. Right, because in this situation, right, the electrons are still independent from each other. R1 and R2 are still independent. We've just lost information, right? They're no longer distinguishable anymore, but they're still independent. So what we're going to do is we're going to take this independent electron approximation, and now what we're going to do, because we can track one each separately, we're going to turn on the interaction between them and integrate it and see what the energy of that repulsion is using this approximation. And what we're going to see once we calculate that energy, we're going to get to the experimental value within 4 eV. We're going to be at something like 80 eV, right? We go from being off by 30 eV, and by antisymmetrizing the wave function, we've done nothing else. We're still dealing with 2 hydrogen-like electrons. That's all they are. But by antisymmetrizing them and turning, and that allows us to turn on an interaction, we'll find that we'll get our approximation really close to the correct answer. Right? And going from that 4 eV error to getting exact is a much harder process that will require us to do something better than just hydrogen orbitals. We'll have to be more clever with them. Okay? So I'll talk about that next class. Talk about that strategy. Right? We've antisymmetrized. How do we do better from there? We'll talk about that. And that will give us exactly the framework. This framework of antisymmetrization gives us the framework on how to build molecules of individual atoms. We're going to mix, instead of psi 1 and psi 2 being electrons on a single atom, they're going to be electrons on 2 different atoms that are coming closer together. And we're going to interact 2 electrons from 2 different atoms and antisymmetrize the wave function of both of them together. And we're going to find that that forms, if everything works out for us, that forms covalent bonds. Okay? So this antisymmetry property is essential for forming bonds. You don't form bonds without this. Okay? So this is our critical mistake before. It's not our fault. It's just the way the math works, unfortunately. So what we'll do next class is come back to this equation, do that integral again by turning on the interaction, and see how close we are. Once we do that, we can move into molecules. Okay, have a good one, guys.
Found it's all shiny. I was like, we're not gonna see it. I just found like 6 of them because I keep losing them. And then I go, babe, I lost something.
I'll see you in like half an hour or something.
Yeah, it probably won't be that long.
Okay.
I just have to let's get it counted and then.
No problem. I'm there till time.
Well, you should leave a little book taunting at the grill.
Oh, I get it again, don't I?
Yeah. I don't know why there's.
Because they love me. They heard my call. I missed it last time.
It's really, they're during acceptance days, they're always there.
Yeah.
Oh, are they?
If you ever show up on a weekend that there's an acceptance student day, I have like 50.
So I was here on the first acceptance students day and I went to go get a burrito and their plaid didn't work. They couldn't take card. They only took vouchers.
Yeah.
I got my burrito for free.
Oh,
Yeah,
perfect.
they're like, you can just have it.
Come find me. I have like a stack of vouchers.
Or come
Oh,
find me, I work
yes.
for admissions.
When's the next acceptance students day?
There's not
No
any
more
left this semester,
But
but
next spring.
Will the vouchers work for next spring?
yes, they
Oh,
don't
yeah,
change.
They don't
Oh,
change.
yeah, you should definitely do it.
I've been collecting.
I don't, do they do them for the open house? I don't remember.
They don't.
I
So
don't
no more
remember.
this spring, but next spring I will have vouchers.
All right, cool. Thank you.
Because I'm in jazz band.
I love free food.
No, really.
You just want the jazz
Hey,
band,
if you
you'll
guys got meal swipes at the end of the semester, hand them over to me too.
find- Ella has extra.
can
If you want to
swipe
talk to
it.
her. Thank you.
Bye, take care. I will eat your meal swipes for sure.